So let's look at the relationship between pressure and the number of particles. So when we did the pressure and number lab, or PN, and we graphed our data, we found that our data had a positive linear trend. So if this is our pressure and this was our number of particles, we saw that as we added our number of particles, our pressure increased. So as our N increases, so does our pressure. And if we decrease our number of particles, our pressure is going to go down. And eventually, it'll intersect at 0, 0, because if we have no gas particles, we can't have pressure. If pressure is a measure of particle collisions with the sides of the container, and you have no particles to collide with the sides of the container, you're going to have a pressure of 0. So this should have been a positive linear relationship with a y-intercept close to 0. And that tells us as our number goes up, our pressure is going to go up, and as our number goes down, our pressure is going to go down. So let's look at two different problems to focus on this relationship. Okay, so here is our first example, and our first example says you have 5 moles of gas in a sealed container. The pressure is 2.6 atmospheres. What is the pressure if you release 3 moles of gas? So we have our table here that has all of our different variables. We have our initial, our final, and our change. So we know from the problem that we are only focusing on pressure and our number of particles. So we are going to ignore our volume and our temperature for right now. So let's start plugging numbers in. We have 5 moles of gas. So that's our initial N is 5 moles. In a sealed container, the pressure is 2.6 atmospheres. So 2.6 is our initial pressure. So we have 5 moles of gas, has a pressure of 2.6 atmospheres. What is the pressure if you release 3 moles of gas? So we're looking for pressure. That's what we want to try and find. And we're releasing 3 moles of gas. Now, it doesn't say we have 3 moles of gas left in the container. We lose 3 moles of gas from the container. So if we started with 5 and we lost 3, we're left with 2 moles of gas for our final. So we have 2 moles remaining. Okay, so now we're going to plug in our changes. And remember, we're going to use arrows to do this. So 5 to 2 means that our N is going down. We know that from our relationship, if our number of particles goes down, our pressure is also going to go down. So we know that that will decrease. So now when we set this up, since we're looking for pressure, we want pressure to be our final answer, we're going to start with our pressure number. So we're going to start with 2.6 atmospheres. And we're going to set up our change factor, the thing that's going to change our pressure. And since we want this number to get smaller, we want our smaller number on top. So we want 2 moles over 5 moles. So since I have my smaller number on top, that means this number will go down. Now, all I need is my calculator. 2.6 times 2 divided by 5 gets me a pressure of 1.04 atmospheres. Now the question is, does that answer make sense? Well, our pressure was supposed to decrease because our number of gas particles decreased, and 1.04 is smaller than 2.6. So yeah, that number makes sense. Remember, you can always do this both ways. You can flip these numbers and see which one makes sense. If we did 2.6 times 5 over 2, we'll get a bigger number. We get 6.5. Now, if I had gotten that as my answer, and I went to go back and ask myself, does that make sense? 6.5 wouldn't make sense for a pressure. If my number of particles is going down, my pressure should also go down. Going from 2.6 to 6.5 isn't a decrease in pressure. That's an increase in pressure. So this one is not right. So we know that our final pressure is going to be 1.04 atmospheres. Let's look at a second example. So this example says you have a container with 2 moles of gas and a pressure of 3.1 atmospheres. You add gas until the pressure reaches 5 atmospheres. how many moles of gas are in the container. So again, we're just focusing on pressure and number, so we can ignore volume and temperature. And we're going to start plugging in what we already know from the problem. So we have 2 moles of gas. So that's our initial N. And it has a pressure of 3.1 atmospheres. So that's our initial pressure. You add gas until the pressure reaches 5 atmospheres. So 5 atmospheres is our final. How many moles of gas are in the container? So that's what we're looking for. So now let's do the change part. Our pressure went from 3.1 to 5. So is that an increase or a decrease? That was an increase in pressure. So it's going to go up, which means that our number of moles also had to have gone up. In order to increase the pressure, we needed to add more gas. So since we're looking for a number of moles, that's what we're going to start with. So we'll start with 2 moles. Set up our factor. Since we want 2 to get bigger, since we want it to go up, we're going to put our bigger number on top and our smaller number on the bottom. So since I wanted my number of particles to increase, I needed to put the bigger pressure number on top. Then I'm going to do 2 times 5 divided by 3.1, and I get 3.2 atmospheres. Or, nope, wrong units. Not looking for pressure. Looking for moles. So in order for my pressure to go from 3.1 atmospheres to 5 atmospheres, I had to go from 2 moles of gas to 3.2 moles of gas. So that's how you'd solve pressure and number type problems.